What's up, people? Okay, so this video is going to talk about acid-base reactions and what we see happen to an acid once it does its acidic thing and what we see happen to a base once it does its basic thing. So this is where we are going to talk about conjugates. All right, a conjugate is going to be the resulting product that forms after the acid does its acid thing and a base does its base thing. So a conjugate acid is the product that forms as the result of gaining a proton, which remember is the same as an H plus. And a conjugate base is what forms as a result of losing that proton or H plus. So I like to think of those little like read along videos where it's like follow the bouncing ball as it goes from word to word to word. It's going to be the same thing, but we're going to follow the bouncing hydrogen. All right, so here we have HCl and H2O, water. Okay, and those two things are going to react with one another. And it's going to form on the product side a hydronium ion and the chloride ion. So what happened? HCl donated a hydrogen over, not H0, goodness, donated a hydrogen H plus over to water. And the result is that this acid, once it lost its H plus, forms a conjugate base on the other side. Okay? And then what we see is water acted as a base here. It accepted the hydrogen and it formed H3O plus on the other side. So on the product side, it formed a conjugate acid. So what we can end up seeing is that on the product side, you can also see that this H3O plus could donate its hydrogen over here, and then this whole reaction could be reversible. And that's where we're going to start to talk about reversible reactions, those two-headed arrows. All right, so a conjugate acid-base pair is going to differ by an H plus. All right, so if you have your donating acid, it is going to form a base that does not have one. And your base is the H plus acceptor, where on the other side, guess what? It does have it. So you have to look at both parts of the reaction in order for you to see who the acid-base pairs are. And again, here you see the double-headed arrow because this can go back and forth in equilibrium. Sometimes it's written this way, but most people end up writing it this way just because it's easier and faster. Okay? So, a conjugate acid-base pair always differs by the H plus ion. Conjugate acids have one more H plus. That means one more H, and you have to change the charge. Okay, the conjugate base, however, has one less H plus. That means you remove an H plus and you remove the charge. So you have to know how to get in and around zero. Now, as you saw in that first example, water, which we think of as neutral, acted as a base there. And there are substances that are considered to be amphoteric. Amph meanings both. Okay, so these substances can act either as an acid or a base. It's like that friend that you have that acts one way around one group of people and acts another way around another group of people. So if water is going to be around a bunch of bases, it's going to act like an acid. And if it's going to be around a bunch of stronger acids, it's going to act like a base. So you might see that it forms OH minus and it also forms your hydronium ion. Okay? We all have those friends. We know who you're talking about, right? Right. Yeah. Is there? Okay, so here we can see an example of water acting as a base. All right, it's in the presence of, this is a fictitious substance, HA, general equation, and water here is going to act as a base. So this means that this is going to be a pretty strong acid because it's going to force water to act as a total base. So we end up seeing that it forms a minus on the other side. This is the conjugate base. And water acting as a base on the reactant side is going to accept that hydrogen. And on the other side, look, there it is. This is the conjugate acid. Okay, and you end up seeing it can go back and forth. All right, the same thing is true, but in the opposite way when we end up seeing water act as an acid. Okay, water is in the presence of a stronger base. And ammonia isn't even that strong of a base, but it is stronger of a base than water is. So here you see its lone pairs right there. It's going to rip off one of those hydrogens. It's going to donate it so that NH3 on the other side, the conjugate acid, is going to be, oh, look who it is, ammonium. Hey, ion friend. And our water, since it lost that hydrogen on the other side, the conjugate base is going to be hydroxide. All right? So yeah, ions are so important. Okay? All of these acid-base interactions um, do show that we have some way to um, make them not as bad, okay? Meaning that we can neutralize them. I'm trying to explain neutralization without using the word neutralize, okay? So you can actually get really wickedly strong acids that completely dissolve and make your hydronium ions, and super gnarly strong bases that completely form OH minuses. But those two things together make something benign. All right, so HCl, hydrochloric acid, ugh, NaOH, Drano, really bad, ugh, they look at a nice double replacement reaction where we get NaCl, which is a salt, and water. Look at that. Okay, do you remember when we were doing double replacement reactions and I asked you the three questions? Do I make a precipitate? Do I make H2O? Do I make H2S gas? Well, this is why we were asking about H2O, because that formation of that molecular compound is going to be a driving force in the completion of our reaction. Okay, so neutralization reactions are where your hydronium and your hydroxide ions form water and salt. It doesn't mean it's always going to be NaCl, okay? Remember that. A general term for any substance could be a salt, our ionic compounds. So it could be like a reaction of MgOH taken twice and HNO3, and you are going to form H2O and magnesium nitrate. Magnesium nitrate is a salt. That is not balanced, but you get the idea. Okay? So the applications of all of this are going to be great because we always know that acids and bases are going to pop up in our environment. Okay? Acid rain is probably the most famous, infamous of the whole thing. Okay, all rainwater is slightly acidic, and we already talked about that when we did our special synthesis reactions. Okay, way back in chapter 8. So in the synthesis reactions, if you have a non-metal oxide gas and you bubble it through water, you're going to make an acid. And that's exactly what happens. Okay, especially with any of the nitrogen monoxide or dioxide, carbon dioxide that is produced, SO2, SO3 gases, you are going to make acidic rain. But this has us majorly questioning about our carbon footprint, what kinds of things we're putting into the air, and seeing the effects of our acid rain on stonework. The first picture was taken in 1908. 1908, and the second picture was taken in 1968. And obviously you can see that the face is completely dissolved with the acidic rain. So I always like to show these pictures right here because this really helps show what we're doing. So the cleanest rain usually ends up having um, a pH of 5.7. So don't think of it as needing to be 7.0. But here we are in Abington at a nice 5.2. So we're not too bad. But you'll end up seeing that where it ends up being a little bit red around this region right here, in this region, and this region. I mean, mainly it's this region right here is going to be the lower levels. So why is that? Well, there's a couple of reasons. We know that the jet stream is usually going to flow from left to right, meaning west coast to east coast, and we're going to basically get all of the dirty stuff. But also, do you know what is produced a lot in this area right here? I'll show you. Okay, there's going to be a lot of coal produced, which is going to be when we're going to have a lot of production of those non-metal oxide gases. And you can see that that all is like right here, which is pretty much the exact same thing. Yes, in spots over here and there and everywhere, but it's no coincidence that those two things are going to align. Over on the West Coast, where we end up seeing the cleanest uh, rainwater is where they have hydroelectric power and where they're going to have other kinds of renewable resources. So that's why they have better pH than we do over here on the East Coast. Okay, facts, people. Gotta look at the facts. All right, so that is our conjugate acid-base definitions, amphoterism, neutralization reactions, and talk a little bit about acid rain.